Welcome to an exploration of nanofluidic diodes and rectifiers, where we'll discover how nanoscale channels can control ion flow like electronic components. Just like electronic diodes control electron flow, nanofluidic diodes control ion movement through nanoscale channels with remarkable precision. Let's start by understanding what nanofluidic diodes are and why they matter. Nanofluidic diodes are nanoscale pores with asymmetric properties that allow ions to pass more easily in one direction than the other, rectifying ionic current. The key difference is that electronic diodes use semiconductor materials, while ionic diodes rely on charged surface interactions with ions in solution. In the forward direction, cations are attracted through the negatively charged pore easily, but in reverse, anions are repelled, creating the diode effect. These nanopores typically range from 1 to 100 nanometers in diameter, small enough that surface charge effects dominate the physics. Now here's where things get interesting. The simple PNP model often fails to predict real behavior accurately. When a charged surface contacts an electrolyte solution, it creates an electric double layer of counterions that shields the surface charge. The double layer consists of a compact stern layer of tightly bound counterions and a diffuse layer where ion concentration gradually returns to bulk values. The Poisson equation relates electric potential phi to charge density ρ through the permittivity. The Nernst-Planck equation describes how ion concentration Ci evolves due to diffusion and electromigration in the electric field. The ionic flux Ji has two contributions: diffusion driven by concentration gradients and drift driven by the electric field. For small ions like sodium or chloride in water, the diffusion coefficient is typically around 10 to the minus 9 square meters per second. You might ask, how do we calculate the actual current through the pore? The total current I is the sum over all ion species of their charge times the integrated flux through the pore cross-section. Let's examine the characteristic current voltage curves that define diode behavior. The current voltage curve shows classic diode behavior: high current in forward bias when voltage assists ion flow, and low current in reverse bias when voltage opposes it. We quantify diode quality using the rectification ratio, defined as the forward current divided by reverse current at the same voltage magnitude. The rectification ratio R equals I at plus V divided by the absolute value of I at minus V. Typical rectification ratios range from 10 for modest asymmetry to over 1,000 for highly optimized nanofluidic diodes. Now here's where things get interesting. The simple PNP model often fails to predict real behavior accurately. The PNP framework is a mean field theory that assumes ions don't interact except through the average electric field, but real systems show strong nonlinear effects. The double layer consists of a compact stern layer of tightly bound counterions and a diffuse layer where ion concentration gradually returns to bulk values. The characteristic length scale is the Debye length, lambda d, which depends on temperature, dielectric constant, and salt concentration. For example, in a 1 millimolar salt solution at room temperature, the Debye length is approximately 10 nanometers, comparable to pore dimensions. The geometry matters tremendously. Conical or trumpet-shaped pores with narrow and wide openings create strong geometric asymmetry. In a conical pore with negative surface charge, the narrow end creates higher electric field concentration, leading to stronger rectification effects. The standard theoretical framework for modeling these systems is the Poisson-Nernst-Planck equations. The PNP framework consists of three coupled partial differential equations that describe electrostatics and ion transport. First, the Poisson equation relates electric potential phi to charge density ρ through the permittivity. Second, the Nernst-Planck equation describes how ion concentration Ci evolves due to diffusion and electromigration in the electric field. The ionic flux Ji has two contributions: diffusion driven by concentration gradients and drift driven by the electric field. For small ions like sodium or chloride in water, the diffusion coefficient is typically around 10 to the minus 9 square meters per second. You might ask, how do we calculate the actual current through the pore? The total current I is the sum over all ion species of their charge times the integrated flux through the pore cross-section. Let's examine the characteristic current-voltage curves that define diode behavior. The current-voltage curve shows classic diode behavior: high current in forward bias when voltage assists ion flow, and low current in reverse bias when voltage opposes it. We quantify diode quality using the rectification ratio, defined as the forward current divided by reverse current at the same voltage magnitude. The rectification ratio R equals I at plus V, divided by the absolute value of I at minus V. Typical rectification ratios range from 10 for modest asymmetry to over 1,000 for highly optimized nanofluidic diodes. Now here's where things get interesting. The simple PNP model often fails to predict real behavior accurately. The PNP framework is a mean field theory that assumes ions don't interact except through the average electric field, but real systems show strong nonlinear effects. Experimental current voltage curves often deviate significantly from PNP predictions, showing different slopes and nonlinear behavior. At high salt concentrations, ion-ion correlations become important. Ions cannot overlap in space, creating excluded volume effects. Finite ion size creates steric effects that limit the maximum ion concentration that can fit in the nanopore, especially near charged surfaces. The maximum concentration is roughly 1 over the ion size cubed, typically around 10 molar for hydrated ions. Several advanced physical effects must be included for accurate modeling. At high electric fields near charged surfaces, the dielectric constant of water decreases due to alignment of water dipoles, an effect called dielectric saturation. The field-dependent permittivity can be modeled as epsilon of E equals epsilon 0 plus epsilon infinity minus epsilon 0, divided by 1 plus E over E saturation squared. Surface conductance provides an additional current pathway along the charged wall, particularly important in small pores where surface area dominates volume. Current flows both through the bulk solution and along the charged surface, with surface conduction becoming dominant in nanoscale channels. Electroosmotic flow occurs when the applied electric field acts on ions in the double layer, creating fluid flow that drags other ions along. The electroosmotic velocity, UEOF, equals negative epsilon 0 zeta over viscosity eta times the electric field E. One of the most important nonlinear effects is concentration polarization at the pore entrance. When current flows, ion depletion zones form on one side and enrichment zones on the other, dramatically affecting resistance. The depletion zone has lower ion concentration, increasing local resistance, while the enrichment zone has higher concentration, creating asymmetric resistance. This concentration polarization can lead to current saturation at high voltages, where further voltage increase doesn't proportionally increase current. The saturation current is approximately 2 times diffusion coefficient times elementary charge times bulk concentration divided by the diffusion layer thickness. For a typical system with 100 millimolar salt and 10 nanometer pore, saturation current is on the order of 1 nanoampere. To improve predictions, researchers have developed modified PNP models incorporating these effects. The Bikerman model modifies the Poisson equation to account for finite ion size, preventing unphysical ion concentrations. The modified Poisson equation includes a factor 1 minus nu times the sum of concentrations in the denominator, where nu is the ion volume. Dynamic Stern layer models allow the surface charge to vary with local potential and ion concentration, capturing charge regulation effects. You might wonder why we need all these modifications to a seemingly simple model. The answer is that nanoscale physics is fundamentally different from bulk behavior. Surface effects dominate, discrete molecular structure matters, and mean field approximations break down. Let's look at how these nanofluidic diodes are actually fabricated and measured. One common method uses track-etched polymer membranes, where single-ion bombardment creates damage tracks that are chemically etched into conical pores. Last, nanopipettes are pulled using heat, similar to patch clamp pipettes in biology, creating well-defined conical geometries. The measurement setup uses silver-silver chloride electrodes in solution on both sides, applying voltage and measuring current with picoampere sensitivity. Typical measured currents range from picoamperes for very small pores to nanoamperes for larger structures, requiring sensitive electronics. These nanofluidic diodes have exciting applications in various fields. Researchers are building ionic circuits with logic gates, creating fluidic computers that operate with ions instead of electrons. For example, an ionic AND gate uses two nanofluidic diodes in series, producing output only when both inputs exceed threshold voltages. Nanofluidic systems can harvest energy from salinity gradients between seawater and river water, converting osmotic pressure into electrical power. Single nanopores can detect individual molecules passing through by measuring transient current changes, enabling DNA sequencing and protein detection. Asymmetric nanopores could enable more efficient desalination by selectively removing ions while minimizing energy consumption. Despite progress, several key challenges remain in this field. We need better multiscale models that bridge from atomic-scale molecular dynamics to continuum transport equations. Fabricating nanopores with precise, reproducible dimensions and surface chemistry remains difficult, especially for mass production. Many applications require long-term stability in harsh chemical or biological environments, which can degrade pore properties. Let's work through a concrete numerical example to estimate rectification ratio. Consider a conical nanopore with 10 nanometer diameter at the tip, 100 nanometer at the base, and 1 micrometer length. The surface has negative charge density of 10 millicoulombs per square meter, typical for glass or silica. We fill it with 10 millimolar potassium chloride solution at room temperature. First, calculate the Debye length using the permittivity of water, Boltzmann constant, temperature, and salt concentration. This gives a Debye length of approximately 3 nanometers, which is comparable to the tip radius. At the 10 nanometer tip, the double layers from opposite walls overlap significantly, creating strong cation selectivity. In forward bias, with positive voltage at the base, cations flow easily from base to tip, giving roughly 100 picoamperes at 1 volt. In reverse bias, anions are repelled by the negative surface, giving only about 5 picoamperes at -1 volt. The rectification ratio is 100 divided by 5, giving a value of 20 for this geometry and conditions. Real experimental systems often show even higher ratios due to concentration polarization effects, not captured in simple estimates. Let's summarize the key concepts we've covered about nanofluidic diodes. Nanofluidic diodes use asymmetric surface charge distributions in nanoscale pores to rectify ionic current, analogous to electronic diodes. The Poisson-Nernst Planck equations provide a useful starting framework, but often fail to quantitatively predict real behavior. Important nonlinear effects include ion-ion correlations, finite ion size, dielectric saturation, and concentration polarization at pore entrances. Modified models that incorporate these physical effects provide better agreement with experiments. Applications span from building ionic circuits and logic gates to energy harvesting from salinity gradients, to biosensing single molecules. This field beautifully combines fluid dynamics, electrostatics, and statistical mechanics at the nanoscale where all these physics become intertwined. Thank you for exploring the fascinating world of nanofluidic diodes and rectifiers, where nanoscale physics creates macroscopic device functionality.